courses. And, so it was a bit of a privilege and quite a push that he gives to students. It all started with Claude Coupeau, so I don't know if any of you know Claude Coupeau, who's known for results in cryptography.
Teleportation?
Teleportation. And yes, so I was looking for an advisor and he said, oh, I met this guy in London. He's a nice guy. I was looking for somebody who could, well, a good advisor, an advisor. And then I went in his office and he was so happy. I met a few other prospects, advisor, and so they were, yes, I take students, but they were like, and Prakash, oh, and that student, yes, I have this thing that I need to. And I was there forcing him to speak French because I was so shy to speak English at that time. Okay, so that's it. I would cite myself and say that I've used up all my nice words in this book. So.
I don't know if anybody knows the incident to which you're referring, but she was giving a talk at Lix in 1998. And Von Pratt started asking difficult questions at the end, and she said, "I'm sorry, I have used up all my English words."
Subject a little different from what others, but maybe it's somewhat related to what Katusha talked about and maybe Gordon too. It's a joint work with a colleague in Laval University, a student, and starting collaboration with Stephen Chong and Scott Moore. And so I've translated, I made a French translation of PrakashFest. So it is the first word of the birthday song that we use in Quebec. It means so the song says my dear Prakash, it is your turn to let you well, like hear people talk about love. So that's more like what you're hearing now than what your birthday.
Merci.
Okay, so yes. So the context. So there is this advice that Prakash gives when you give a talk. Never apologize. But I should say that I just realized that I was talking before lunch, so I thought I had 1 more hour to settle a few strains, but anyway. So the idea is we want to enforce security by controlling information flow. So the big picture is that you don't want private information to influence public information, so that public observer would deduce things about private information. So static mechanics, like usually are type-based and they are conservative. The reject program in case of that. And so non-interference is satisfied if so. I just said that. So the non-interference is the property that the variation of data, private data, does not influence low security levels. You may have many security levels. So non-interference cannot be enforced by purely dynamic approaches. You cannot say, well, I have tests everywhere and we will enforce this. So I'll give examples. And you could think of monitors and rewriting. So our approach, it's a type-based, so we do first type-based static analysis. We analyze a program, so it's a program-based framework. So if the program is safe, it means that all the executions satisfy non-interference. If the program is unsafe, so it's not well typed, it's unsafe, so it's rejected, and the program may be unsafe. So instead of rejecting those uncertain cases, we mark them as uncertain, and then we go for a dynamic analysis. So we instrument the code, so insert tests when it is needed, not everywhere. So the execution then will do these tests, and maybe can stop the program if a leak is dynamically detected. So the approach is flow sensitive, so variable security type can change over time, and communication is through channels. So unlike many, so there are other approaches that are flow sensitive, but not all of them. And so the progress sensitive, so that's the part that is from this collaboration with John and Moore. So we prevent also leaks due to diverging loops and to the safe stopping of the program. So I give the language, and then I'll give a few examples, and so it will be a hybrid presentation, in fact. It's static and dynamic. And more dynamic than I thought. So it's a very simple language. So we receive a value from a channel, and we send value to a channel. So that's how communication is made. So you have, so the variables are local. The observer don't see variables, but of course he can deduce some values because of what he sees through the channels. So you can read the channels that correspond to your security type or below. So an initial typing is given for every constant channel. So that's how security is. So that's the nice thing of doing a flow-sensitive approach. So the variables that you use in your program are not relevant. It's just the channels that you mark as private or public. So, for example, you say that screen in the cafeteria is public. This keyboard, what entered in this keyboard is private, and so you just have these constant channels that you mark as a private or not, and then your program. So you can change these and your program just is done as in a natural way. So program as sequential. I said that, and observer can only see the low channel, so I said everything. So now it's the part where are the lines here? Maybe I should. Here, sorry. So I want to illustrate, so maybe it will be a little elementary, but at least you understand that. So of course, so the basic thing is that you want to reject, so I'm talking statically now. I'm given a program and I want to statically analyze if this program should be accepted or not. So of course, you would reject such a program, send a high value to a low channel. So I will use these keywords, low value, to mean private, high. So what about if your X is inside an if statement? Well, in this case, you also want to reject this send, right? Because it would reveal the value of this H, which would be high. So suppose H is a high value. So this is so the way it's done is that the block
So you assume the attacker knows the program, right?
Yes, thank you. Yes, you should ask question if I forget to say these things. Yes, then, yes, and so suppose yes, now, it's for the complex, and now, yeah. So this is, so what I'm saying now is known, it's standard things. So here will be another implicit flow weak. Yeah, so if so this variable x is public value, it's an integer, it's low. But depending on the condition h, you will set it to 1 or 2, and then if you send x to a low channel, you will reveal the value of h, of course. So, this you conclude that an assignation must be analyzed inside with respect to the context it is in, and also it tells you. No, that's it. So now, suppose I do the same thing with the channels. So I have this if high condition, then the channel, the low channel, else a high channel. It's not exactly the same thing. What I wanted here is to change, so the second part of this example was to say, okay, let's suppose here I put a high channel, and let's suppose that this condition is low. So does it change anything? So you will reveal nothing about the condition. However, if the condition is false, you will end up in this branch. And then, so you must get out the if and decide what is the type that you should give to x. So in one branch x is low, and the other branch x is high. So the normal way, the usual way is to say, well, let's be pessimistic, we have no choice. So let's say that x is high, and then you reject this send.
Can I interrupt, Josée?
Yeah.
You have reached the limit of what's visible on the board because it's blocked by these computers.
Ah, okay. Thanks. So I can continue talking about that?
Yes, but up slightly above.
Yeah. And then, so what I will do is that okay, so what happens if I do the same thing? So I can be pessimistic here. What happens here? Suppose I want to send x to C, a high variable here, to C. What should C be to be pessimistic? So when I get out this if, I have to decide which security type this C must be given. So consider that. So having in mind that there's a send to C here, you would think that I should put C as a high type. However, what if I first receive something from C and then send this to a low channel? decide that X is C is H, I receive something from this private channel, so this X should be private, right? I send it to a low channel, so no. So I cannot allow that. So there's no way you can be pessimistic here. In one situation, you would like pessimistic would be to set C to low, and in the other situation, you would set it to high. So the solution is, of course, to mark this as uncertain. Okay.
Don't you reject the program then?
No, so yeah, so that's we don't reject the program then. We mark it as uncertain, and then we insert some tests that will check dynamically if the program can be is fine. So yeah, so it's just I should have put a low condition here. Sorry, because then yeah. I won't see the details, but a low condition works here. Yeah, so you mark this channel as, in fact, a channel that is that's the notation that we use. So it receives, so a channel as so it has two security levels associated to it. What it receives and the variable itself, the value of the variable itself. More place here. So C here will be.
That's invisible.
So C will get. So it will be an int, uncertain content, and the variable itself here is low because the context is low. So, and then when you will instrument, so basically we only reject the program when there is a send. We only reject, is that what I said? We reject the program when there is a send, dangerous send, or send that is statically surely bad. And otherwise we instrument, so we had some tests to before the send to make sure that it will be fine. Yeah. So there are three security levels: low, uncertain, and H. So value types, integers, and channels that contain integers. It's not a big restriction. So the security level form a lattice, low, uncertain, and high. As I said, the constants are given types as given. And then, what about this less than or equal in the presence of uncertain label? So if X, so as we saw, if X is sent to C, we want that at least that the type of C is less than the type of X is less than the type of C. The type of the content of C. So, but less than, what does it mean? Yeah, so we define two other pre-orders. We have this surely less than, where either you are less than, no, not either, but you are less than, and you are not, yes, that L equals U. So why? Because, so it's sure that L is less than U is less than H, that's fine. But then L less than L is also okay. So sending an L to a low channel is fine. Sending an uncertain channel value to a high channel is fine, no matter the value of u. But what you don't know that could happen is you don't want to take for granted a UU. HH is fine. Okay, so this is not surely less than or equal. And the other order that we define is the maybe less than or equal. And then it's simply that you're not, so L prime are not HL. So L low will be maybe less than U and H, and you will have U maybe lower than or equal to L, because at runtime maybe this U will become an L, but it could become an H, so that's why you have to insert tests to check. And similarly, you have UU, and you could have H less than or equal to U. Okay. And this is, so this gives these typing rules. I won't explain all of them, of course. But let's point out that when you send something to a channel, you're really sending three information. So the information of the context, as we saw, like when this condition was sending its value. So you send the context. So the context must be less than the content of your channel. Okay. You're sending also, of course, this value. So its security level should also be less than the level of the channel. And finally, you're also sending, with some other example, the value, security level of the channel itself. So in the typing system, you have, so this is the only place where you would reject a command. It's if you don't have this less, well, not this place, where you don't have the make less than or equal to. So the way you read that is that you have an environment, this is the context, and this is, don't worry about that, and this is the environment that you return after having updated your variables. So here you see with the assignation, what I showed you, the type of X must be the type of what you assign it to, supremum with the context, as I said there. And yes, so you start with an empty environment, a low context, and if you succeed in typing the program, then you say that it is well typed. Yeah, so many other work, they would reject a program when there are bad assignations, and often it's just because that it's not flow sensitive, so the variables are marked as high and marked as low, and as soon as you assign a high variable to a variable that's supposed to be low, you get rejected. So here we only reject when we send something. So we may have many bad things happening, but as soon as we don't send anything on the low channel, there's no problem. So this send. So if the value, the information that we're sending to it may be less than L, so the command will be accepted, it will be instrumented, but if, yeah, but, yeah, so that's my next slide. So we will test the condition dynamically for and hence security levels must be represented by variables in the output program. So we must, in the instrumented program, you must keep track of all of your security levels. And yeah, so here is the dynamic security memory that assigns security level to special variables that we introduce. So you must introduce, so for every X variable of the program, you need to add a variable for its security level, for every, and for its content. So for the channel, you have this, a variable for this, a variable for the content that you must have. So these are these val and CVAR appears there. So the approach is to pass the program to the typing system. You instrument C, and you use crucially the information that you've collected statically. And in fact, we do this in a single step, instrumenting while typing. And then after that, you clean the code using partial evaluation to remove the things that you had that are not relevant. And then C is a wild-type program. If C is a wild-type program, then the instrumentation of C satisfies progress-sensitive non-interference. So I said that I talked about non-interference. So starting with two memories that are low equivalent, so that contain the same values, the same that are equal for low variables, you get out the program with memories that are still low equivalent. So the fact that the value may differ on high variable does not have an influence. But progress is also something that could influence that could leak information. And so I give you this example. So if H10, so suppose here there is a while loop, while true, you skip, and then you send something. So even if you send a low information on a low channel, the fact that this while loop will get stuck there. If H is true, you will get information about H. And similarly, if dynamically you have instrumented your program and then you go through, you're executing it, and you get to a send that was unsafe, and then that you had your conditions, and you check your condition dynamically. If you stop the program there, you must make sure that you cannot deduce things about what could have been the condition to get to this reject. Yeah, so if I replace this while true to skip with an unsafe send here, I have the similar example. So that's what I'm almost done. That's what is encoded in these other things that we compute at the Telepin. So then I had this the same slide at the beginning, just doing this summary. So it's a type-based analysis. So if the program is safe, all the executions satisfy non-interference. If it's unsafe, we reject it. And otherwise we instrument it, and then it's checked dynamically if yes, and some future work so allow some controlled leaks, like, so the easy way is to have some budget, so saying we leak for 1, 2, 3 or 4 times, like this password thing that when you enter your password 3 times, then at some point you get stopped. The classification should be kind of natural, because you just change the the constant value of your channels, and concurrency. So in particular in concurrency, if anybody wants to chat about that, I have some ideas of extending this to concurrency. And yeah, I didn't write it, but allow some control leak through also, as you talked about, how do you call that? No, but you talked about differential privacy.
Yes.
Yeah, it's another way to control leak. Let a little bit go. Yeah, so thank you.
Just one quick question.
It's supposed to be open. You said this magic word, differential privacy, at the end, so are you contemplating a probabilistic extension of all this so that you can reason about things like differential privacy, this probability?
Yeah, I guess it's the next step that you should do. I'd be happy to.
Visit me in Montreal again?
Yeah. Great. So yeah, so if you have any, if anybody has suggestions to how to bring me back with this stuff to probability.
Okay, let's thank our speaker again. So the next talk will be given by James okay. Talking about semantics for the topological calculus.
Yes, thanks a lot. This is a constantly changing title. So by now it's Topological games for the world. So the constantly changing title might indicate that this is still to some extent unfinished work. But I wanted to present it anyway for several reasons. So for one reason is because I think it's about the duality, and I think duality is something Prakash likes very much. Then the other thing is there's a vague connection to turtles, but I'm probably not gonna make this precise unless somebody asks me. And then Prakash also likes turtles very much. And then this is joint work with Nick Bezhanishvili, in fact. And I'm not saying, and Prakash likes Nick Bezhanishvili very much. But I'm saying that, so the way I met Prakash was basically together with Nick at Empirical Observatory. And this is kind of also a good reason for presenting joint work with Nick here, I think. Yeah, so let me, like everybody, briefly mention, so I think I know Prakash very few years so far compared to most of the other people in the room. So from 2010, so we invited Prakash to give a talk in our logic seminar at Imperial College in 2010, and then there was this immediate flood of emails from our colleagues that they want to meet, and we have to move the seminar to another day and to another day. After a long discussion, finally we managed to find a date. And then we were very happy to see this connection with automata theory and duality he presented, and yeah, so it was very nice basically. And so in fact, so this is what I wanted to say, so the special thanks goes here, because for example, I know Nick since 10 years ago, and we never managed to write anything together until Prakash pointed out that in fact we are interested in very, very similar things. Yeah, we shared an office, I think, for 6 years. And I also lived in the same apartment as him. Okay, good. And then the other thing I wanted to mention is that I wanted to thank him for paying my trip to Buenos Aires to present this paper, because I had some trouble finding the funding. And yeah, being a great source of inspiration and fun. Okay, so let me go back to the technical part of the talk. So it will be very basic, but I hope on the positive side that you will get something out of it. So let's see. So I'm going to talk about topological semantics or model calculus and about fixed-point games, as I said. And the goal is to design an evaluation game for a specific type of semantics for the model calculus. And so when I say here topological semantics, I immediately want to make this disclaimer, which I had previously also. So cryptic models based on topological spaces we're talking here about, and not the topological semantics of the model we calculus in terms of. So we are talking about cryptic models where box and diamond are interpreted as just using the relation, rather than box and diamond being interpreted as some topological operators. So just to keep it straight. Because it seems that some people, and several people are interested in something different when they hear this. So the semantics of a formula, the basic idea is just that we want to restrict the semantics of a formula to an admissible subset of the model, not just to any subset. And so far we only looked at some basic setting, but I think it could go further unless somebody stops me. Anyway, so okay, let's see. What's the model with calculus? I wanted to briefly mention what we're talking about. So it's modal logic, just basic modal logic, which box and diamond. We have proposition variables and just the Boolean operators. And we have a mu operator and a nu operator. And important here is just that we push the Boolean operators to the propositional level, otherwise the games for the modal calculus. I mean, this is makes the games of the modal calculus easier to define. Okay, so this is the setup. And the mu operator can only be applied to formulas, and the nu operator likewise, where the variable p we are talking about occurs positively in the formula. Okay. I guess most of you know everything about modal calculus, but I just want to talk you through this anyway. So how do we? So mu and nu, that's probably what you definitely know, is that mu should be somehow least Fixpoint operator, and nu is the greatest Fixpoint operator. So what does it mean, Fixpoint? Well, we have to interpret our formula somehow using operators. And so for a given formula and some cryptic frame and evaluation of this cryptic frame, we can define an operator delta Vp, where this is like the operator in P, so to speak, which maps a subset of U to the semantics of the formula delta, where we interpret the variable P using that subset. I guess this, in some way or the other, anybody has seen this. It's always a pain to write this though, and to read it probably as well. Anyway, so in that way we get an operator from the power set of x to the power set of x. We know that this is a complete lattice. We also know that delta, if it only contains positive occurrences of p, gives rise to monotone operator. And then we can say, okay, the semantics of nu p delta and nu p delta is just given by the least and greatest Fixpoints. So far, so familiar. So now we want to switch just to interpret those formulas using admissible subsets of our model. So instead of just arbitrary subsets, we want to say a formula should correspond to a Klopen subset. That's what I'm going to talk about today. But I think there's much more to say after we have a better look at it, because you should define more abstractly what admissible means here, because you could. Okay, but for now let's just think about Klopen subsets, and I will technically say what the setup is in 2 slides. For now, I just want to say is that, in fact, to go to this semantics has like 2 types of motivations. So I would say the Klopen semantics probably had more mathematical considerations, because if you look at the Klopen semantics of the model nu calculus, it becomes more amenable to techniques from duality theory. In particular, we know that then, completeness with respect to the Klopen semantics is relatively easy to prove. However, I know that people from the model nu calculus side of things will say, yes, but this is the wrong type of semantics. But so there are two fighting, not fighting, but at least arguing, constructively arguing camps of scientists who would say, okay, so it has an advantage because it gives you completeness, it has a disadvantage because because it's the wrong type of semantics. And then also not only completeness, but we also one can study Southwest theorem for semantics, and this has been done. So I'm talking here about things which in fact have been studied already. And then besides the purely mathematical considerations, you could think about a notion of reachability in the limit, where you want to say that, but so basically I spent yesterday evening to make this example precise, but I think I cannot really make it precise, other than drawing this line here. And that's it. No, okay. And okay, suppose you have to...
I cannot see it.
You cannot... so far it's just a line, right? Okay, so suppose you are in some kind of model. For some reason I call this 0 and 1. And suppose we have like something here, and this would be thought of as this turtle. And now the question is, so if we keep the coordinates fixed in the coordinate system of the turtle, so to speak, and we let Achilles run, like in the first second, if he runs 10 times faster than the turtle, he would somehow reach 0.9. And then you look at the tenths of the time interval, and he would reach from 0.9, 0.99, and so on. But he will never reach, using this number of steps, I mean this kind of sequence of steps, he will never reach the turtle basically. But you could say, what you could see is that if he would start at some position 0 plus epsilon and use the same sequence, then the same sequence will easily lead him in the final number of steps above 1. And so that's why, so basically from every position here you would have a reachability, and I mean I would have to define now what the reachability relation is completely in this model. I could do this, but it leads to some amount of technicalities. Anyway, so you could reach in the final number of steps the turtle from every point here. So we also would want to reach it from here, because we don't want to have. So this was this argument about, we've had a lot of probabilistic talks where there was this thing about stability of this notion of bisimulation. And so that's a bit of the same flavor. Although I have to say that this example is more and more clearly emerging, but it doesn't fit in exactly what I'm going to talk about. But I know how to fit it there, but it's just... Okay. So there's a lot of related work already on this cloak and semantics. But if you want to... Sorry, do we know when I started?
You started 10 past.
Okay, thanks. Okay, good. So I just want to say, for now, we just very basic setting here. So it's the what's called extremely disconnected stone spaces. So what is this? It's just basically that the closure of any open set is open again. And now, if you know what this is, if you know this a bit more closely, then this is basically exactly requiring that this lattice of clopen sets is a complete lattice. So far that is just a requirement. You can ask me later if you want anyway about some other options. But okay, let's leave it like this. And the frames here are just, because we have stone spaces, we can just look at the frames. They are now coalgebras for the Vietoris functor. So, in other words, descriptive general frames, if this means something to you as a logician. And so I don't introduce this now, but the basic idea is here just that you want to make sure that the boxes and the diamonds preserve clopenness of your semantics. So you have to make sure that the modal part of your logic sticks to the admissible semantics. And then the model now is just a frame plus a clopen valuation. So propositions are interpreted as clopen subsets. If we don't do this, we are really doomed from the very beginning. Okay, and now formulas are just interpreted as clopen subset. It is said for the purely modal formulas, this is taken care of by the Vietoris functor. Actually, somebody yesterday claimed that it's called Vietoris functor. Who was it? I forgot. Anyway, I think it's Vietoris. Okay, so then the other thing is, Now for the fixed-point operators, we just note that with our definitions, this is a monotone operator and it's a complete lattice, so that's just fine. So we again have the semantics. And that's the semantics that these papers which I showed you previously on the slides, these papers studied essentially. Although we are a bit more restrictive in the
Is this the main reason you picked extremely disconnected spaces?
okay, I can tell you what the main reason is why we picked it, because we need a complete lattice.
Yeah, that's what I want. That's the why.
Yeah, that's the why. However, so if we just coming back to this example, if you would want to look at this example more closely, then we would move probably away from stone to compact Hausdorff, and then we would go either to regular open or regular closed subsets. It's still a matter of debate, I think. But these lattices are not very much different. So mathematically, I think in the example it's more natural to go to the regular closed subsets. In any case, we could do this, but we didn't write it. So, but we need a complete lattice, and I will show you. So, okay, 1 second. So I wanted to say that this Klopen semantics has been studied. However, we are a bit more restrictive because we really want to ensure that we have a complete lattice. Because there's something which is a bit more general, which is called modal mu algebras and modal mu frames. And there you have two types of modal mu algebras. The one of the first and the one of the second kind. I don't know if it means anything. No, okay, the one and the ones of the first kind. So the thing is, you can just require that those fixed points exist. You can just say they exist, and then the least and the greatest fixed point. But then you don't need necessarily a complete lattice, but you need a complete lattice to approximate the fixed point. That's exactly what's happening now. And why do we want to approximate a fixed point? Because if we cannot approximate a fixed point, we cannot define a game semantics. So the whole endeavor of this talk is that we wanted to characterize this semantics using games. Because usually if you especially move away from the purely abstract setting to more concrete examples, it's better to have the semantics characterized in games rather than just abstractly. I mean, everybody who knows the modal mu calculus knows that the games are a very important tool. If you doubt this, you can discuss it later again. But so I wanted to say that, so we need the fixed point approximation of a complete lattice. So how do we approximate the fixed point? Well, the least one, we start with the bottom element, and then we just go up the sequence. I think
It should be an alpha, right?
which one?
On the right of the second equation.
Oh yeah, sorry. Otherwise we had, yeah, no, you're absolutely right. And this should be also.
Otherwise you've already got a fixed point.
The fixed point is always alpha plus 1 for an unknown alpha. Okay. Yeah, you're right. Sorry for this. And yeah, but the other ones are fine. So for the limit ordinals, you take the join and the limit. Okay. But we know that this in both sequences will converge to the least and the greatest fixed point respectively. So now we go, so the whole story, the story of the talk is now just characterize the semantics and describe using games. Now I don't know, those people who know the mu calculus could tell me now whether this, well maybe not now, tell me secretly later whether it's true or not. But okay, let's first attack this problem step by step. And so first we just look not at the mu calculus but just as fixed point games, because this is the main part of the story. So all the games I'm talking about now are just two-player draft games, and the players are called Eloise and Abelard. And the board positions are partitioned into their respective positions, and so the plays can be infinite. So whoever owns a position has to move. If he cannot move or she cannot move, then that player who can't move loses. If such a position is never reached, then there's some conditional infinite games, which is usually specified using parity conditions. But in these fixed point games I'm going to describe, it's much easier. It's just one player always loses all the infinite plays. But the most important bit about it is that if you have these conditions, you always have that one of the player has a history-free winning strategy. This is very important if you want to argue with those games. Now we have this very basic fixed-point game, which you might know or might not know. So basically we are on this lattice power set of X, where we have meet and join just intersection union, and we want to have a game such that Eloise has a winning strategy in the position if and only if that position is an element of the least fixed point. Okay, and so how does it work? So we start in the position we are talking about. Then Eloise has to provide a subset such that X is in the operator applied to this subset. And then Abelard challenges her with one element out of that set. So Eloise at X picks a C such that X is in F of C. And then Abelard just picks one of the elements of the set. So the smaller she can make the set, obviously, the better for her.
Sorry, that's not what you wrote for me.
No?
The move is the C, and you said she...
So this is basically the set of possible moves. So she moves from any, he moves from C to any element of this one.
it's a set of moves.
It's a set of moves, yes.
Okay, thank you.
Yes. And then we can easily show that Eloise has a winning strategy. Sorry, I should say now that this game proceeds in rounds. And in the least fixed point game, Abelard wins infinite place. And the greatest one, Eloise wins infinite place.
When you say infinite, you're allowing for ordinals there rather than just omega, right? Because the least fixed point may not be attained at omega.
No, I'm just talking about omega.
So you're talking about a game that has omega steps, but the UF might be characterized by an ordinal bigger than omega.
Yes, so maybe we come into this in I have a sketch of the argument here, how this works. So suppose X is in the least fixed point. This means that there exists an ordinal, indeed it can be very big, since that X is in this approximate. Now let's see only the limit ordinal. Then we know that X is in the join here, which happens to be the union. So at X, in fact, Eloise can play this union by the definition of the game. And though Abelard now has to pick an element out of that set. So what happens now is that he has to move to some f nu beta where beta is smaller than alpha. And so in general you can always show that whatever happens, so whatever the alpha is, Eloise has now a strategy to prolong the round to come to a position where she is in some f nu beta where beta is strictly less than alpha. And now you know by the well-foundedness of the ordinals that you only can have if there is if it is indeed in such an approximate, you will just reach the bottom of this chain infinitely many steps. Okay, and similarly you can show that for the converse, Abelard just has a strategy to always stay in the complement of the fixed point. And now what happens in the spaces? In the spaces the following is happening. We now have the meet and the join doesn't anymore correspond to union and intersection, but to the interior of the intersection and the closure of the union. And then we just, if you look at this, and if you looked at the argument which we saw before, the possible consequences for the game are just that, so in order to show that X is in the fixed point, Eloise only has to provide a set C, such that X is in F applied to the closure of C. So that's one of the ways of looking at it. And the other one would be if she chooses some open set, such that F is in the closure of that open set, then Abelard should only be allowed to challenge her with an element of that open set, and not of the closure of it, because we still want to continue walking down this line of ordinals basically. And so if you have these two observations, you could easily define now those two games. which characterize this fixed point. So the one is just that you say at position x, Eloise chooses some arbitrary subset such that x is in f of u for all clopens containing this subset. And then Abela answers just with an element. But that's one way to go. And the other one would be to do this one here, where she now plays, in fact, a clopen subset, such that x is in f of u. So this is a, yeah. But now he should not be allowed to challenge her with an arbitrary element of u, because otherwise you could just loop on the join. But he has to play a clopen neighborhood, so to speak. He cannot really pick one element, but he can just cut out a clopen subset, which has a non-empty intersection with the original one. Basically, okay, the way this is done here is in fact, so at u, he picks some element, he picks an element, but also a clopen neighborhood of that element. And now Eloise can pick an arbitrary element of this set here, so he cannot pin her down to one particular one, but just to some clopen set. And now both of those games, I claim, characterize the clopen least fixed point of the operator. Now the question is obviously, why two games? Now, okay, so the one answer is just because it makes the proof of the adequacy of it, of the semantics for the Mykrakos work. However, you can argue, okay, you just didn't understand it properly. And I cannot exclude this completely, but I want to observe that there seems to be no transformation for the strategies in this game from the first game into the second game. So if she has a winning strategy here, there is no obvious way to directly transfer this into a winning strategy. The only way is to say, if she has a winning strategy here, then the x is in the least fixed point, and then we know that there must be a strategy here. But this is the way to how this is used, basically. And unfortunately, then there's even more to come, because you have the two more games for the greatest fixed point. Okay, I think I'm about to exhaust my time, but I wanted to show you the result of all this, basically. Namely, so if the goal was for a formula and a model, we wanted to define a game, just said Eloise has a winning strategy at the position formula, position, if x is in the semantics, in the clopen semantics. Now, normally how this is done is, you could write it down like this. You don't have to fully read the slide now. I just wanted to point out that so this is the usual game for modal formulas. In the very end, there's this kind of clause for unfolding the fixed point. So if you reach a bound variable p, then you just have to unfold it and go back to psi. And well, okay, so this is a completely trivial step in this game semantics for the standard Mykrakos. And then you need this winning condition of infinite place, which I'm not going to discuss. And now the game for this other semantics is just slightly modified for the fixed point case, where whenever we reach basically such a bound variable, we cannot immediately unfold, but we first have to, one of the players is required to choose a clopen subset around the current state, which then again can get challenged by the other player. And intuitively, the mu formulas get more difficult get easier for Eloise, so Abela has to provide more options, and the new formulas get easier for Abelard, so Eloise has to provide more options for him. And so this is then, the game itself is extremely straightforward in a way. And then you just can prove that this is adequate for the semantics. Okay. And then I just want to say that the future and ongoing work is just to understand this better, to look at other topological spaces, and I don't see any problem. At least I know for sure that you can do the fixed point games on complex house of spaces and regular open. The reason why we didn't really look at with the logic, because then the Boolean operators get less nice. But okay, so there are other notions of admissible subset, not necessarily topological, we want to look at. And in general, the game semantics should give you some automata corresponding to your formulas. that's kind of one of the big things you can get. And yeah, so the other two things, shedding light on completeness, the modal recalculus. And if some of this works for creepy frames, we can look into Kolchberg variants. Okay. And that's it.
Time for just one quick question.
So you weren't here the earlier part of the week, but there was a lot of talks on duality in the spring school. Space is extremely disconnected. Stone spaces we're talking about a lot. They're called Stonian spaces. And they arise in the theory of T-star algebra as a significant way. But I did want to ask this question too. So do you really have a convergence theorem of the kind you hinted at there that says something that you can reason about the limit?
So the convergence would be rather that if you compute, so you can define just a relation here, which is the smaller equal relation restricted in some way. So you can only look a certain amount of steps ahead. And then you just see that if you take the semantics, then the topological closure would end this point.
But you don't have the logic, the kind of infinitary rule that tells you about.
No, there's no rule in the logic which would do this. No.
Well, you'll probably find the next talk very relevant then.
Okay.
So the next talk will be given by Radu.
We should thank Clemens again.
Oh, sorry. This talk will be given by Radu Mangaden. It's wonderful title from a dominant way in future in topological semantics.
Congratulations for the
The
project.
latest questions about this topic.
Yeah, this is a little bit. I don't understand what the slides are. Oh, okay. Okay. Yeah, so, well, this is a talk for Prakash, so I have to be at the right level. So I think I should start by telling you the story of how I met Prakash, because it's relevant for everything. It was, I don't remember the year when Calco or CMCS was in Udine. So that time I was, yeah, I was a postdoc in Italy, in the worst research environment you can imagine. Well, it is true, I was depressed, I was sure that my career will end before starting, and I met Prakash in a random discussion, which essentially changed my life. I mean, after that discussion with him, I found the straight of redefining my life, redefining my research, and so on and so forth. I'll never have sufficient words to thank you for that. And since then, somehow we remain in touch. We start working together much later. But in all the important events in my life since then, I asked Prakash to support and advise and so on. And one of the important events that happened a few years ago when I applied for this fixed position in Aalborg. So I was preparing my documents for the application, and in the call I was supposed to give possibly a paper which was not published yet, in which to demonstrate my research vision. So I thought one thing I'm working with Prakash would be very good. So we had this Skype discussion before the deadline. We start discussing about this, but then we end up by discussing the paper itself. In Denmark was evening, so I went to bed. I didn't know that Prakash was working on that thing. So overnight he contributed to my research view, and this is what I submitted to the... Well, I got the position, but this is what the commission evaluated. So now...
I was not in the committee.
It was the only contribution. No? So about the talk, I'm not going to bother you with showing you again the results that I got with Prakash in the last year. Many of you already seen them repeatedly. I'm going to show you what you've never seen about these results. So essentially how this flow of ideas went, and I think some of them are interesting. That's why I choose to rephrase Kant's title, because here a few people the other days spoke about distances on Markov processes. And everybody came with some kind of arguments why one is good, why is bad. So the word prolegomena means an analysis of the very basic preconditions that can allow you to answer to a question. So what I would like to argue here is if it is indeed possible to have this kind of distance and if it is some kind of canonical choice for this distance, because the main argument is that this distance should very much replace the concept of bisimulation, which is a canonic thing that we understand it very well. The trouble is that we have many such distances and we don't really know which is good and which is bad. So I'm going to try to make an analysis, not telling you which is good and which is bad, but telling you what I think are the answers that whatever answer you can give to this question should satisfy. What are the recommendations? Yeah, so in fact this story started here in Oxford. This is in Lambeth Flags, I think it's called, the park. Prakash was, yeah. I remember that when we take this picture, Prakash was enumerating all the fields medalists. So I don't know why. This is in your famous office here somewhere. So here is where we started our discussions about what I want to show you. But I want to go fast. So the ingredients of this entire discussion are, of course, the concept of Markov process, as defined by Prakash and his co-authors. Yeah, so we have a measurable space. Then we take some kind of distribution over this measurable space. They can be probabilistic or not. It's not very relevant for what I want to show you. And in general, a Markov process is just a mapping, a measurable mapping between the space, the measurable space M sigma, and the measurable space of the distributions on M sigma. This is definition. Then the concept of bisimulation is, I think it's correct that it was introduced in '98. So you take a relation, an equivalence relation, and you consider just any measurable set which is closed under this relation, and two points are bisimilar if and only if the values by this theta correspond in each such set. Okay. Then on the other hand we have the logic. Here I name my Markovian logic because this is particularly important for what I want to say, but there are a few versions of this logic. This logic with exactly this syntax, in fact it was introduced by Aumann, and it was introduced for Harsanyi type spaces, which are mathematically speaking the same thing with Markov processes, only that developed by a different community. So here you have the Boolean operators, and in addition you have these special modalities indexed with rational numbers. So M satisfy LR phi if with at least, let's say, probability R, I will hit a state satisfying phi if I leave from M. That's the intuition. And M does the same. If you are in the probabilistic settings, between L and M there is a kind of De Morgan relation. If you are not in a probabilistic settings, that's not the case. So if you are in subprobabilities or you are in general rates or whatever measurable things. So this is the kind of logic you have. And then what's interesting is that this logic characterizes indeed the bisimulation. Oh, sorry. And then when I met Prakash, it was actually just proving that, propose a complete axiomatization, a weak complete axiomatization for this logic. Why I insist that it's weak? Because this logic is not compact. So, and the problem of strong completeness are actually open for a very long time. Goldblatt was the only one proposing the solution, but in his solution he was assuming Lindenbaum lemma as an axiom, and then has also other strange traits from a model theoretical point of view. So this is the framework with which we started cooking our research program. Okay, so now a bit about these distances. I'm thankful to the other speakers because they motivated very well the other day's story. So it is obvious that bisimulation is too fragile, as the other said. So we need something which will tell us the things better from the point of view of similarity. So for instance, if this E is very small, I'm rather expecting these big things to be much closer than these two other things. Obviously, 2 by 2 they are all non-bisimilar. So this is how the concept of bisimilarity distance appeared. This will be the first argument. So all the papers agreed on the fact that two things, if they are bisimilar, there must be a distance here. But after that, they are starting not to agree anymore. So, for this reason, I'm trying now to find some kind of important arguments to understand in which direction we should go. One argument is that all the time we are speaking about probabilistic or stochastic systems, we should be aware that there is no such thing in universe as probabilistic or stochastic system. So, well, I don't want to become ontological now, but still, I don't believe that the universe is really probabilistic. What we are doing probabilistically is organizing our information about the universe. So this means that the outcome, which is the probabilistic system, is the result of the way I'm organizing the information about the universe and not how the universe behaves. So this means that I have to be very careful on how I'm defining these probabilities. Because if tomorrow I buy a better microscope and see better what happens there and calculate better probabilities, I should be still able to say if what I predicted yesterday will remain true or not. So in this sense, I think it by itself speaks about a natural topology that we should have behind any kind of epistemological approach to this problem. We have to be aware of the fact that better and better and better and better approximations of these systems, which obviously means better and better numbers there, should induce a kind of a convergent behavior. So I think this must be one of the main arguments for saying that such a distance is a good one. So if you see here, I'm expecting to see that this system is in fact the limit of this sequence of systems. Okay, so this will mean that in the open ball topology induced by such a distance, I'm expecting to prove this. But not all such distances are good, because if I take the stupid one which says 0 if they are bisimilar, 1 otherwise, obviously this sequence is not even Cauchy. So already this distance has the property that the kernel is bisimilarity, so it satisfies the first condition, but it stops there. Okay, so this is the second argument. The third argument, and this happens a lot in science, I'm taking these models and then I'm trying to check properties which are important for me. And then, if I'm saying that the property is satisfied for all better and better and better approximations, I believe that is true for the limit. Well, could be this true? The second one, I might even think that I can organize more fancy thing and I can speak about a convergence on logical properties. And I believe that if these systems converge to that limit, these properties converge to that limit, and if I can prove that Mi satisfies Fi, then on the limit M will satisfy F. Well, with Prakash we prove that both things are already false for that very basic logic I showed you before, which doesn't have temporal, until operators and so on. And whoever knows a bit of topology realizes immediately why this must be true. So this is a paper we had in 2012. So for the probabilistic case, if I take this logic which I showed you before, so here I don't need M because it is a De Morgan wall of L. But if I'm calling positive properties all the properties of this type, where I can have as well M, and L minus all the negation of these kind of things, you can easily see that if F is positive, then this is closed in the open ball topology induced by the distance, while if it's negative, it is open, and in the other cases we didn't manage to say much. If you change the settings and you go to subprobabilities or to general distributions, the situation is much more complex, and in fact we identify here a bigger hierarchy of things. So here I'm taking L plus as before, I have LR and MR but not negation, while L0 doesn't contain M. So it is now a difference, topological difference between L and M. What we discover is that if F is positive, is 0 positive, so it's without M and without negation, then indeed this is closed. Of course, its negation will be open, but if it can also involve M, then it is not closed anymore. It's actually a countable intersection of open sets. Yeah.
So what is D here?
Sorry?
What is D? Or what is
Just any pseudometric that will have the simple property that the kernel is bisimilarity. Okay? So all these kind of things shows that indeed, if you are taking this kind of properties and you are proving that the infinitely better approximation of the system satisfies the formula F, still doesn't mean that the F is true at the limit. So this again is the core of a lot of logics used by people for studying stochastic systems, for instance. You want to prove that the system oscillates. That was a kind of a fancy question that people were asking when I used to work with system biology. And there, you have no way of saying what oscillation is without involving negation and without involving them. Why? Because you have all the time stochastic noise, so it is not that oscillation look like this, oscillation look like that, so you have to describe a kind of area, and to describe this area you have to have approximation from below, approximation from above, negations, all the kind of stuff. So obviously if you prove that better and better approximation oscillates, doesn't mean that the system oscillates. So, well, bad news for some people are good news for others. So we are happy at that moment with the results, but of course we only started to ask ourselves what can be a condition that after all will answer somehow this. And again, here our question relies on the fact that we want this topology or distance or whatever it is to behave very, very much like bisimilarity from a mathematical perspective. So try to understand the pattern, the mathematical pattern of this entire story and see what is happening if we replace equivalence with a distance. So this is. So now I'm starting to try to see if I can define such a condition. And of course, being this similarity I propose you, I'm starting from the definition of bisimilarity, of bisimulation. So this is the definition. Well, the first attempt is to say, okay, what I want to say is that if MP converges to M in the topology induced by D, well, I'm expecting that for any measurable set S which is close to bisimilarity, the probability of going there of MK converges to the probability of going there from M in the topology of reals. That's the first choice, which is obviously wrong, because if you look to this example, the probability of going from M1 to M is 0 all the time, while on the limit the probability of going from M to M is 0.5. So obviously this is not a good answer. And what's more important is to also observe that the coinductive nature of this definition is here. The fact that S must be closed under the relation R is where the coinductive nature lives. In this thing which I just proposed, there is no such a coinduction nature. So now, of course, I have to think on how to put the coinduction inside. So the second one will be, okay, what I will have to say, I will have to say that this set S to which M converges with this probability, for this set I can for itself find a convergent set of sets, a convergent sequence of sets, which probably will converge in some kind of topology induced by a distance which has to do with the distance I'm starting with. In this case, I will propose the Hausdorff. And now we have the coinduction, because it will stay here. The fact that I'm looking to this convergence, to that convergence, but already the convergence between this and that is where the coinductive step is hidden. Well, this is wrong again, because of this quantifier. So this constant sequence, again, is a counterexample. This means that actually we have to replace that universal quantifier with an existential quantifier. So this means that a distance now is good and we call it dynamically continuous if the following thing happens. If I have a sequence of a system which converges to that, what must happen is that for any measurable set S which is close to bisimilarity, I'm going to find a sequence of such sets that converges to S in the Hausdorff distance induced topology, and moreover the probabilities converge in real. This was good, but the question is now what is the relation with bisimulation, because it's not very clear anymore, it's not so obvious. Well, what we discovered, it was a bit unpleasant. So I'm starting again from bisimulation. So now I'm going to make some modification to this relational definition of bisimulation to try to mimic what happens on the other side. Okay, so this is the first one. The second one, I will do the following thing. I will say, for any S, exists an S prime such that S and S prime are equal. But I prefer to write them in this relational format. So S and S prime are equal, and between theta ms and theta ns prime exists again equality. Now if I replace these two equalities with two binary relations, arbitrary binary relation, I can define something which will be called, let's say, xy bisimulation. So what is x is a binary relation on measurable sets, y is a binary relation on real, so now I have an xy bisimulation relation. Okay. So now a classic bisimulation is nothing else but an equal on sigma and equal on r bisimulation. Okay, I'm still not there. Now I can go even upper and take arbitrary, such relation of arbitrarity. So for just any arity k, I'm going to define such a relation. And now the definition is like before. Well, if I do this, and I'm doing it for arity omega, I'm finally getting something which mimics indeed what happens with the dynamic continuity condition. Which is in a sense, bisimulation puts in relation objects. Now I need the similar concept of bisimulation, which doesn't put in relation objects, but put in relation a sequence of objects with their limit. Why this was not very good for us? Because first of all, from a algebraic perspective, it's a nightmare. It's not as nice, beautiful span or cospan or something. But that's not the only reason. The worst reason is that this distance, the stupid one, 0, 1, is still dynamic continuous, because the only sequence which is Cauchy there is the constant one. So we are unhappy with this result. So Prakash proposed to try to look in a different direction, and is when he found and invited Dexter to join us, and the thing started now to move towards duality. So we thought that since we have, after all, understood this completeness of those logics and all this relation in which bisimulation plays its role on both categories and so on, we should try to investigate what happens on this kind of duality and see if we can mimic this. So, well, long story short, we prove this, I call it classical now because I will have also an extended one, stone duality for Markov processes, but to do that we had to identify a special class of Markov processes, which is defined like this. I'm not taking just any measurable space, but I'm starting from a special topology, which is Hausdorff, is zero-dimensional in the sense that it has a countable base of clopens, which must be closed under Boolean operation, under this LR-like operation. But it is not compact, because the logic is not compact. It is, however, saturated in the sense of model theory. So if we call this a stone Markov process, a morphism of such Markov processes will be just a morphism of Markov processes which is continuous and preserve this designated base of clopens. So if we do that, and then we go to the logic side and we try to understand from a Boolean perspective what this logic means. Well, in the meantime, we will also solve the strong completeness problem, but that's a different discussion. So we introduce this new algebra, which we call it Aumann algebra, to honor Aumann, who was the first one doing this kind of stuff. So what is an Aumann algebra? It's just a Boolean algebra which in addition have this kind of LR operators. And these are the axiom. Observe that this is an infinitary axiom. That's where the non-compactness is hidden. And of course, a morphism of such algebras are just morphisms of Boolean algebra which respects the LR operators. So we prove stone duality, and the idea is like this. If I'm starting from a Markov process with designated base, I take the designated base, that's an Aumann algebra. If I'm starting from an Aumann algebra, I take the ultra filters, but not only the Boolean ones, but also the ones which satisfy all those axioms, including the infinitary ones. I will be able to construct a stone Markov process. So this is the duality. Okay. This was presented to Lix last year. Okay, so what did we learn from here? What did we learn from this duality is that exists an intrinsic relation between this base and essentially between the topology induced by this base and the bisimulation. They have a certain kind of relation. And we try to understand if this relation can give us something interesting about the distance. And actually it does. And this is an interesting theorem that I want to discuss with you. So what this theorem says is the following, that when I have the pseudometric, I have essentially two topologies over the same space. One topology is this almost stone topology, which is giving me the duality. The other topology is one induced by the distance. But because of those topological results that I showed you before, that not just any formulae are closed sets in the topology of the distance, this means that these two topologies must not be identical. But the relation between these two topologies is actually the key of understanding how we should really speak about this distance. And this is a theorem which Dexter proved. And what it says is the following. If I'm taking a stone Markov process, so here I have the base. Of course, this base induces this almost stone topology. And I have also a pseudometric. Then, if I'm taking one element and I'm looking to the diameter or all clopens containing that element, that goes to 0. So this condition is equivalent to saying that the topology tau b induced by B is actually defines the topology of the distance. Or another equivalent is that pseudometric is continuous in both arguments with respect to the topology tau b. Or another one is that if I'm picking up two objects and I'm looking to the distance between them, this distance will be the infimum of the diameter of all clopens containing. So these are the equivalent ones. And this opens us the door for the next level of the duality. Moreover, each of these conditions enforce what I called before dynamic continuity. That part of the argument might be not so obvious actually. It's a bit complicated to prove, but it is true. Okay, so now we propose you the concept of metrized Markov process. So metrized Markov process is just a stone Markov process, like I showed you before, which is devised with this pseudometric that satisfies this axiom M, which is one of the equivalent conditions which I showed you before. Well, you can define morphism of such things, and what's more important, you can define isometries of such things. Okay? On the other hand, if I go to Allman algebra, what am I expecting that Allman algebra to do? Well, there are some axioms here, but those are not important. The Allman algebra, which is metrized now, has a concept of a diameter of a form. And what is the important axiom about this is that if I'm taking an ultrafilter U, the infimum of the diameters of all the formulae in ultrafilter must be 0. Because it must point to only one point, topologically speaking. Again, I can define morphism of such things and the isometries of such things. And now the interesting thing is that we can extend the representation theorem. Exactly the representation theorem that we had before with the same mappings now are in addition also isometries. So if I'm starting from an Allman algebra with this concept of diameter, I'm going to the Markov process constructed with ultrafilters and then back with the base of clopens, I will get the same distance and the same diameter. And the other way around, I'm starting from a distance between two Markov processes. I'm going to the Allman algebra, I get the concept of diameter, and then back with the distance, I recover the same metric space. So these are the two versions of the representation theorem. This we will present it to MFPS. So this is what we understood by now. I don't want to conclude this talk because I'm sure that we will have a lot of things to not publish further. But I want to say happy birthday, Prakash. I have a lot of other pictures with you which I didn't dare to put them online.
Okay, let's questions?
So, I was expecting future, right? You talked about the past a lot. So, I mean, the future that I would see is to
Do you dare to see it?
Well, if I did like that, yes.
Yeah, actually initially I wanted to put a philosophical section on this, and the philosophical section has to do with non-founded sets. Because there is another perspective which is very interesting. Remember that by simulation for non-founded sets is exactly what identity is for well-founded sets. So now if I'm trying to relax the concept of bisimulation, since bisimulation are the basic bricks which are giving me any kind of alectic predicates I can construct about the theory. This means that whatever axiomatic approach, for instance, to arithmetic is very constructive in a way. But maybe if you look to the duality, and if you look not necessarily for a pseudometric, but for a topology of truth, you can see why arithmetics is incomplete. It's incomplete because the axiomatic approach is trying to really dig in a constructive manner all the things which are true, when in fact the truth might be very much of a kind of topological nature. And maybe by a historical fact, my mathematics is defined by now axiomatically. Maybe that's wrong. And actually, Rasiowa and Sikorsky had this kind of arguments in their book regarding the identity. But Rasiowa and Sikorsky didn't know about bisimulation, didn't know about non-founded structure. So maybe there is something still to go into that direction. Well, Markov processes are a good excuse since everybody is interested in distances these days. But I think I see something below this. But it's philosophy again, so you can kill me now.
Other questions? Okay.
So, yeah, I have a question. But later. No, sorry, back.